Hello everyone. Today I'm gonna talk about new topic, masses and weight, section 5.3. And as you might know, mass and weight are not the same thing. Mass is the intrinsic property of an object, while weight is a force. Okay, weight. So it's a unit for the weight. The mass is a kilogram, and then unit for the weight is a Newton, right? And then mass is a quantity that describes an object inertia, and then its tendency to resist being accelerated, right? And then again, weight is a gravitational force exerted on an object by a planet, basically, the Earth, which varies from weight planet to planet. So the weight is simply mass times the gravity, 9.8. Okay, so weight is different on Jupiter than the Earth, but mass is the same because the mass is again intrinsic property of an object. It's a value never change wherever you are. But weight again is a force. And then G in general 9.8 is what? Is for Earth, right? Everybody know the gravity for the moon is much 7 times smaller than the Earth, right? So then G of the moon will be smaller. So the weight of the moon will be smaller than the Earth as well. Okay, so sometimes we use the pound, but in general we use Newton only, right? And then kilogram is we can use pound, a gram, but for physics we will only use Newton and kilogram MK as units. So your G value for the Earth is a 9.8 meter per second squared. So what is the weight in Newton and the mass in kilogram of a 70-pound gymnast, right? So then you see 90-pound gymnast, you can see you can convert 90 pound to kilogram simply. Then you see the mass will be 41 kilogram, right? So then now you can find the weight of it, right? 90 pound, you have a 150 pound, and then 240 pound. Each of them have a 41 kilogram, 68 kilogram, and 110 kilogram. So the weight is simply this number times 9.8, and this number times 9.8, and this number times 9.8. But basically, you can use 10 for gravity, for this course, okay, which simplifies your calculation. Okay. And then another term, new term here you will learn is about the apparent weight. So the weight on the object is the force again of gravity, right? Your sensation of the weight is due to contact force supporting you. So in other words, the normal force, the contact force will be your apparent weight. And in other words, normal force or the contact force is gonna be your sensation of the weight, right? So let's define your apparent weight, WAPP, in terms of force you feel. So weight apparent is magnitude of a normal force, which is the definition of the apparent weight. Then I will give you the example in the elevator later. So for example, if you take if you are, the man, assuming you are inside the elevator, and then you are basically, first floor, and then let's assume you are going up. And then once you start, once the elevator start moving up, how do you feel? Right? So close your eyes, imagine your first floor of the elevator, and then elevator, start moving up. How do you feel? So you feel you're heavier than usual. So that's the sensation, right, of the normal force. So which is called apparent weight. Now we can explain it, physically. Now think about the force acting on the man in the elevator. So there are actually two forces, right? So normal force and the weight. So if you use Newton's second law, your vertical force is a normal force minus W. Normal force is acting upward, weight is acting downwards. V equals what? Ma, which is a Newton's second law. So then now you see if you solve this one for n, then you will see n is your weight plus mg, which is weight, right? So then your apparent weight, which is the normal force here, right, is gonna be weight times non-zero ma values. Because why? What is ay? Because you're accelerating upwards, right? So your net force is acting upward. So may is a positive quantity. So basically that means your apparent weight is your normal weight plus a positive quantity. That's why you feel heavier. Okay? So your second next question is your mass is 70 kilogram and he is standing on a scale in an elevator that is moving up 5 meters per second. As the elevator stops, the scale reads 750. So before it stopped, was the elevator moving up or down? How long did the elevator take to come to rest? Right? So then now you see the scale reading. So another thing is we are actually talking about the scale reading, right? Which is a 750, which is what? The normal force, right? The scale reads the normal force, which is again apparent weight. Right? So then our weight, your basic weight, you know, is a 680 Newton, which is a 70 times a 9 point or 10, so roughly 700 Newton. Doesn't matter. Okay. So this is his regular actual weight, right? But because the person apparent weight is a greater than his actual W, which means as you see the previous question, right? Your normal force apparent weight must be weight plus some quantity, positive quantities, right? So that's why your apparent weight for this case is about 15 Newton more, right? So then you learn, previously that the object is slowing, as in this case, because was why the elevator is stops, right? So either it was going up or going down, but the elevator stops. So that means it's slowing down. So its velocity and acceleration vectors point in opposite direction. So the elevator velocity must be negative. So that means it is moving downwards. Okay. And next question. 50 kilogram student again, so his weight is 500 Newton or for 9, doesn't matter, gets in 1,000 kilogram elevator at rest and it stands on scale so you can measure the normal force, right? As the elevator accelerate upwards, so then now you have an elevator and the person with the scale on the scale, right? So elevators moving up, right? So the acceleration is again positive. If your acceleration is positive, again, this case is exactly the same as the case you see here, right? So your apparent weight is again positive. So your MA value must be positive as well, right? So the answer is 8, right? And then second case, the same student in the elevator, rest, bathroom scale. Sadly, the elevator cable breaks, right? What is the reading on the scale during the few seconds? So then now, elevator, person, scale, and then you have a cable. When the cable is not there, broke, what will happen? The scale and the human, fall at the same rate. So there is no contact force by the scale. So your apparent weight is 0. 0, right? And then another, similar question. You have a 50 kilogram student in the elevator. As elevator begins to move, she has an apparent weight of 600 Newton for the first 3 seconds. So again, her normal weight is 500 Newton. And then 600 Newton, that means elevator is moving over, right? So that's why her apparent weight is greater, right? So then now this is a chapter 2 question, right? For the first 3 seconds. So your time is a 3 second, right? How far? So basically you're looking for delta x, right? So then what is your acceleration? You can find your acceleration, your normal force acting upward, right? And then weight is acting downwards, which is a MAY, right? So your normal force apparent weight is 600 and the weight 500. M is again 50 times a Y. So that means your Y is a 2, sorry, this is AY. So AY is a 2 meter per second squared. So your A is 2, time is a 3 second, right? So you can find the distance. And then second topic I'm going to talk about today is about the normal force that we already talked about in chapter 4, right? An object at rest on a table is supported by the table, right? That supporting force is called normal force, right? So the harder the object bears down on the surface, the more the atomic springs push back. So in other words, nothing happened and then you place a cup here and then the curve is at rest. So that means that the two forces acting on the curve is a weight and then normal force. So then the curve is at rest. So you see normal force minus W equals 0. So N is a W, right? So in general, normal force is the same as your weight, right? But however, if you press additional force downward on a book, and then this is the book's force diagram. And then if you use the Newton's second law, F net, this is gonna be what? Normal force up, weight down, force down equals 0. So this case, your normal force is a weight plus your push force. So one, common mistakes I see every semester is that student in general, like this example, normal force is the same as weight. They assume that, but that's not true. It really depends on what's going on there, right? This case, you see normal force is a weight plus the downward force. So never assume normal force is always the same as a weight, okay? And so the normal force on an incline. So for the incline case, the ramp case, the most important thing for the ramp case is you don't use traditional coordinating system. So horizontal x, vertical y, we don't use this. Instead, your x-axis is along the ramp and your y-axis is perpendicular to the ramp. So then again, your normal force is perpendicular to the surface. So it's a long y direction, but your weight is moving, acting straight downwards. So basically this omega W has two components, horizontal along the x-axis and vertical along y-axis. And then we can use the trick. You see omega x is a W sine theta, which is the acceleration along x-axis. And then W cosine theta is acting downwards, which is canceled by the normal force. So for the ramp problem, again, the first thing is how you use a special coordinating system, okay? And then your weight, horizontal weight is a W cosine theta, okay? So two common mistake to avoid, right? Normal force on the ramp, your normal force is not straight up. It's always perpendicular to the surface, right? Your ramp, so it's a slightly tilt. And your weight is not along y-axis, but your weight is always a straight down toward the center of the earth. right? So for example, the box is sitting on the floor on the elevator again. The elevator is accelerating upward. So then what is the normal force? Again, think about the forces acting on this box. Normal force up, weight acting down, right? So then Newton's second law, you can say normal force up, weight down, but this is an accelerating upwards. So this is a ma, where a is a positive number. So in order to have a positive net force, your n must be greater than mg. So the answer is a the box is being pulled to the right at a steady speed, right? So this is what we did last time. Steady speed, what does that mean? A is 0, so F net is 0 as well, right? So in this situation, you have to find the force diagram. The first one is a weight, mg is acting down, and then you have a normal force, and then this tension basically have a two component, Tx, and you have a Ty, right? But the Ty and then plus n minus mg is gonna be 0 because the object is accelerating or moving at the steady speed horizontally, right? So that means your vertical forces are canceled out. So again, you have a F net y is gonna be normal force plus Ty for this case minus mg is gonna be 0. So then now you see your normal force will be mg minus a positive quantity Ty. So the answer is your n is less than c. The answer is c, right? Less than mg. And the acceleration of a downhill skier, the skier slides down steep for 27 degrees. So this is exactly what we did here, right? On a slope, let's assume this data is 27 degrees, right? So you have a skier here, and then the total force acting on the skier is a normal force, and the weight down, and then the horizontal force is a mg sine theta, and then the vertical force is mg cosine theta, right? The friction is much smaller, so there's no friction, right? So this is your net force. So without mg sine theta will be your acceleration of the sphere, right? So the answer, your acceleration will be g sine theta, and then g is 9.8, sine angle is 27 degrees. So you have IAX 4.4 meter per second square. And then, yep, next topic is gonna be friction. And then the other topic, last topic we have is about interacting object, and the last one is a two roughs, right? Okay, so then let me talk about one more topic about the friction, and then we'll finish chapter 5 this weekend. Okay, so the friction force, there are basically two different type of friction force: static friction force and then kinetic friction force. Static friction force, assuming you apply force, assuming you have a very heavy object, and then you're trying to push it, but it's not moving. What does that mean? There are actually four forces: normal force, weight, your push force, and then static friction force. And then because net force is 0, so that means your push force is the same as a static friction force, right? So what does that mean? Net force is 0. So your static friction force is exactly same as your push force. But the question is, what if you apply 10 Newton initially, and your push force is a 10 Newton? So then your friction force is a 10. What if you apply 20 Newton? Then your push force is now 20, and your static friction force is a 20 as well. So what you can see here is your static friction force is not a fixed value. It is a varying depends on your pushing force. So this is a free body diagram. So your definition, static friction force, is a static friction coefficient times a normal force. So static friction coefficient is a property between two objects. For example, the floor and the in the bottom of the object you're pushing. Okay. And then the direction of a static friction is, of course, it's opposite to motion, right? The magnitude of the static friction adjusts itself, right? So that the net force is zero, right? So it's not a fixed value, right? So on a box on a rough surface is pulled by a horizontal rope with a tension T. The box is not moving. In this situation, what is the force acting on? So you of course have a static friction force, normal force, and then weight, right? So this static friction force is exactly same as a tension. So then net force is zero, so it's not in motion. So the answer is a B. And the kinetic friction force, especially you have, unlike a static friction force, has a constant magnitude, which is a mu k times a n. Again, mu k is a coefficient of a kinetic friction. So again, same thing, right? So you have a fk, but this case, make sure the object is in motion, right? Like the object is kind of a sliding, right? So the rolling friction, we'll talk about it later in other sections. So then now you see kinetic friction force, static friction force, coefficient and coefficient and coefficient. You see what happened. Your static friction force coefficient is always greater than kinetic friction coefficient. Okay, and then this is why, because once you start moving something, you have to apply stronger force than once in moving. Okay. Okay, so this case, a box with a weight of 100 Newton is at rest. So then weight is 100 Newton. So it's a normal force is a 100 Newton as well, right? So it is pulled by 30 Newton horizontal force. Does the box move? So then now you have to apply maximum static friction force in order to initiate the motion. So then now what is your maximum static friction force, which is mu s times a normal force. Your mu s for this question is a 0.4. Normal force is 100. So the maximum static friction force is 40 Newton. But you apply only 30 Newton, so the object is not. Okay. So finding a force to slide a sofa. Carlo wants to move 32 kilogram sofa to a different room in a house. She places sofa slider, right, whose kinetic friction force is a 0.08, right? When she push the sofa at a steady speed, what does that mean? Net force is zero. So how much force she applied to the sofa? So then now we can draw the force diagram. The object is moving by this F push. I'll just call it FP. And then, of course, you have a kinetic friction force. And then you have, of course, normal force, which is the same as a weight, which is a 32 times 10, right? Weight is a mg, right? So then now what is your kinetic friction force? Which is a mu k times what? Normal force 320. So this force must be same as a pushing force. Why? Because this is at a steady speed, so net force must be 0. Right? So if you assume the mu k is a 0.08, your answer is simply 0.08 times mg. So this is your force is going to be 25 Newton. Right? The box is being pulled to the right over a rough surface. P is greater than Fk. So the box is speeding up, right? Suddenly the rope breaks. What happened? Because the rope is broken, that means there's no tension, only friction applies. So the net force is acting to the left. So the answer is up, slow steadily until it stops. Because it's like it's like you just push an object and it slows down, right? So the answer is E. Okay, this is it. And then we will have an exam, second exam, sometime week after. So I will, have an announcement soon for the second exam, and then be ready to take it. Okay, make sure I will assign your homework as well, and then you study your homework as well as your lecture materials here, and then read the textbook very carefully. Okay, thank you.